Okay, great. Okay. So I'm gonna open up this. Great, well, I think people probably keep trickling in, but we might as well get started. So welcome everybody to another Infrared Science Interest Group, or IR-SIG webinar. Before I introduce our speaker and we get started, I wanna go over a few instructions, and I should introduce myself as well. I'll be moderating the webinar today. My name is Meredith McGregor. I'm an assistant professor at the University of Colorado Boulder and one of the co-chairs of our IR-SIG group, along with Mike Zemkoff at RIT. So the webinar today, I pasted these instructions into the chat window so you can refer to them later, but I'm gonna read them now so we're all on the same page. When you have questions for our speaker, please submit those questions via the chat window. If that's not already up for you, you can find the chat window by clicking on chat at the bottom of your Zoom window. That's the best way to submit questions. So if you just type your question into the chat window and then click enter, it will come through. At the end of the talk, there'll be a Q&A period, and I will read questions to our speaker. If you would very much like to ask your question directly of our speaker, we can probably have time to do that. And if you're interested in that, I think the best way is to use the raise hand feature. So if you click on the participants menu, also at the bottom of your Zoom window, you can click on raise hand, and a little blue hand will pop up next to your name. And that way I can unmute you and you can have a chance to ask your question directly to the speaker. It's great and helpful if you ask your questions while the speaker is talking. Kevin has the chat window open so he can try and address questions when they come up, or we can wait until the end. You can also submit feedback or comments or questions that you have for the IR-SIG Leadership Council and co-chairs through the chat window as well. I'll save those until the very end of the talk if there is anything. And of course, if we don't get to them during the hour, then Mike or I will send an email response afterwards. You can also report technical difficulties through the chat window. If something's going awry in Zoom or we lose audio, you can kind of let us know that in the chat window. And then the last important point is that this is going to be recorded and available to view later on our webinar webpage, and the link is again in the chat window. So I think that covers basically everything. So it's time to introduce our speaker, and we're very excited today to have Dr. Kevin Cooke, speaking to us today on magnificent constructions, how massive galaxies stop forming stars. Kevin graduated from the Rochester Institute of Technology with his PhD in 2019, and he worked with Dr. Jehan Kartaltepe, who is one of our IR-SIG Leadership Council members, and he's now working as a postdoc at the University of Kansas. So Kevin, take it away.
Great, thank you very much for the introduction and the invitation to share some of my work here today. So today's talk will be a combination of some of the dissertation work that I did while I was at RIT working with Jehan, and some of the brand new work that I've been doing as a postdoc with Alison Kirkpatrick at KU. And so to start us off, the primary goal of the different research projects that I'll be talking about today is understanding where the most massive galaxies developed their stellar mass. So in the present day universe, for massive galaxies, massive being above 10 to the 10, 10 to the 10.5, the local universe is really dominated by these quiescent elliptical type galaxies. And here's a fantastic picture of galaxy cluster Abell S740, where you can see one of these quiescent galaxies here in the bottom left, which is highly contrasted by the spirals that you can see on the right by many different characteristics. Ellipticals have a generally old stellar population, so redder colors, with little to no ongoing star formation, which you can see by the distinct lack of blue star forming regions. And there's this lack of star formation because of the lack of a cold gas supply. So you also see that there's very little obscuring gas and dust in that elliptical there. And the big science question that these projects are linked with is, what are the factors that moderate the growth of these massive galaxies? How is their history of star formation and ceasing star formation moderated by some external and internal factors? And this is an incredibly wide subject area. So to kind of narrow it down so that you know what to expect, there are many different ways that star formation can be temporarily enhanced and then quenched in a galaxy. For example, when two galaxies merge, the compression of both of their gas supplies hitting each other can induce a star formation, which quickly consumes the gas supply in that merging system, leaving behind a quiescent elliptical. There are also many different types of environmental quenching, such as ram pressure stripping, that will remove the cold gas supply from a galaxy as it encounters the hot gas medium within a galaxy cluster. There's also mass quenching, where we see that some galaxies have a lower specific star formation rate as they accrete stellar mass. And finally, there is the process of AGN feedback, where an active galactic nucleus, a feeding supermassive black hole at the core of the galaxy, can emit enough luminous energy to heat and unbind some of the cold gas within the host galaxy. And today, I'm really going to be focusing on this right-hand column, environmental quenching, specifically on very large scales, and AGN feedback as part of some of my new work that I've been doing. But there will be some mentions of galaxy mergers and mass quenching along the way. Now, to go back to this original image that kicked off this discussion, this is not just any type of elliptical. This is a brightest cluster galaxy. And it's this specific population that I have been doing a lot of research on. So brightest cluster galaxies tend to be the most massive and most luminous galaxies in a galaxy cluster. They tend to lie in a relect position in position velocity space within the cluster. And in relaxed galaxy clusters that haven't undergone any recent cluster mergers, this will place the BCG at the heart of the potential well of the cluster. And so while the vast majority of them are passive quiescent galaxies like this, you will get some extreme counterexamples. For example, the brightest cluster galaxy in the Phoenix cluster is having, you can see is much different than the example that I previously showed. And it is experiencing a phase of star formation due to the condensation of gas from the hot intercluster medium, condensing along filaments down the cluster potential well and into the BCG. And then that dense gas supply can form stars. This is one example of what's called a cool core brightest cluster galaxy, where the gas supply within the core of a cluster is cooling down and forming stars within the BCG. But there are additional other examples of some weird cases. This is the object that really kicked off our studies. Grant Tremblay et al. Published this BCG merger image in 2014. And what you can see is that there are two massive ellipticals near the center of this massive lensing cluster, SDSS J1531. And if you look at this zoom-in picture of that those merging ellipticals, you'll see that there are very small, small in comparison to the rest of the galaxy, but these are superclusters of galaxies that are forming stars. Now, in this case, there's about 5 solar masses per year being formed, which may not sound like a lot to some other samples, but in quiescent systems like this, it's very, very high. And each of these superclusters are separated by about 1 kiloparsec. Now, with the discovery of this system and trying to understand how common this type of major merger at low redshift can be, or intermediate redshift, depending on your labeling system, we looked through the other clusters of the Sloan Giant Arcs survey, which 1531 was originally observed in. And we found a second major merger system, albeit with less extreme star formation activity. Here in my 2016 paper, we published images of these obscuring dust lanes surrounding that merging system at the core of this cluster. And what we find is about 2 solar masses per year as measured by O2 emission from the Sloan Digital Sky Survey spectra, which were taken in that green circle that you can see in the bottom left. However, the rest of the Sloan Giant Arc survey, in total 37 strongly lensing clusters, did not show such strong star formation activity. So this type of major merger induced star formation remains very rare in the local universe. So to better understand where all the rest of the old stars came from, we need to look at higher redshifts and actually look at these galaxies' pasts. Well, what should we expect? Well, there's been plenty of work showing that these massive galaxies quenched around a redshift of 1, and their high redshift counterparts tend to be much smaller in terms of spatial scale, this much smaller effective radius than they are today. They're very compact ellipticals instead. However, whatever happens to these galaxies in the past needs to be consistent with an overall quiescent population at low redshift that will still experience some major mergers due to their cluster environment. So how do we look for these progenitors? Well, this is where we turn to the Cosmos survey. So while Cosmos may not have the volume at low redshift to do a BCG study, it does have the volume at high redshift to look at massive galaxy progenitors. Cosmos is complete above a stellar mass of 10 to the 10.1 out to redshift 3, which is great because we'll be able to understand what is happening to these massive galaxies between redshifts of 1 and 3, which is where the star formation rate history of the universe is peaking. Now, we run into the next step, which is Cosmos is a very large survey. It's 2 square degrees on the sky, over 2 million galaxies detected in the public data release catalogs. How do you select galaxies that are most likely to be the progenitors of the massive galaxies that we see today? This is where we wanted to use a selection criteria that did not select on any sort of color or star formation priors, because we didn't want to bias ourselves towards things that were already quiescent or really highly star forming when we want to understand what the full population is doing. So to do so, we rely on something called an evolving co-moving number density method cut, which is a type of a stellar mass cut. And it's fairly abstract, but I'll walk you through first a simpler version and then tell you about some corrections that we apply to it. Let's first imagine that at early times in the universe, you have the universe in a box. You perfectly understand how many galaxies of each stellar mass you have in your box. And you're curious about what the descendants of these galaxies are doing at low redshift, at present day. Well, if you look at one sample of a given stellar mass, I've highlighted an example sample here in yellow, they inhabit a co-moving volume at a given density. As all of the galaxies across the galaxy stellar mass function form stars consuming their own gas supplies with time, they will all increase in stellar mass, they will change in star formation rates, they will change in colors, but won't change is their density inhabiting this volume element of the universe. And so this number density gives you a link between a galaxy population of a given mass at one time period versus another time period in the universe. However, this is a constant co-moving number density method, and just a few slides before, I showed you evidence of something that could throw a big wrench in something like this. Because the universe doesn't have a constant number of galaxies across cosmic time. Galaxy mergers do occur. So what we need is some sort of correction such that when we identify our present day BCG densities, we can look back at a population of a given density that also includes some of the lower mass galaxies that will eventually merge onto the massive seed galaxies that are the primary progenitors. And so we turn to cosmological simulations. Here is a plot from the illustrious simulation showing the number density on the y-axis, redshift on the x-axis, and for a given population of galaxies of a given stellar mass at present day, so we can focus on, for example, the 10 to the 11.5, because those will be very BCG-like, they're very massive. In illustrious, they can identify the less massive merger counterparts that will be merging onto the BCG seed. What that does is it lowers your stellar mass cut and increases your number density cut. And increasing number density widens the parameter space of galaxies that you're selecting, and so you're grabbing more of those lower mass galaxies. This can still be somewhat abstract, so some people are more familiar with a plot like this. While it may look scary because of the number of colors, it's just one thing plotted at many different redshifts. On the y-axis is the number density of galaxies per stellar mass bin per cubic megaparsec, so number of galaxies at a given stellar mass per volume element. And on the x-axis, we have stellar mass. And the redder colors, they're at higher redshift, and as you go towards lower redshift, you see a buildup of the number of galaxies at higher masses, so that you understand what this plot is showing you. We can identify the number density of galaxies that are above this mass cut of 10 to the 11.5, which will be the vast majority of cases be massive quiescent ellipticals like BCGs. Now we have that number density. What we can do is apply the corrections from illustrious to let us know the number density to integrate for other redshifts. And what that does is it gives us a new number to have under this triangle, and that lowers the stellar mass cut for the galaxies that we're selecting. So we're grabbing those lower mass progenitors and also including some of those major merger partners. And we continue to do this process out to redshift 3. So this is great. We now have a sample of brightest cluster galaxy progenitors out to redshift 3 as selected by stellar mass. But one of the critical things here is that we want to understand how their local environment is shaping their star formation characteristics. Are these massive galaxies in these protocluster regions experiencing a change in their median star formation from their counterparts in the field, in low density regions? So great, we have all these galaxies selected by stellar mass in Cosmos, but we need to identify their local environments. And so we use the density maps provided by Behnam Darvish in his 2015 paper, which takes the Cosmos field and in given redshift slices will count the number of galaxies within a given area element of the map and smooth that area element across the entire map. Now, some of you may immediately have the question, well, for a lot of these galaxies in cosmos, we have photometric redshifts. While many of them are very good photometric redshifts that can constrain within a few megaparsecs, so these are large-scale environments we can't discern within a given cluster, for example. How is the photometric redshift probability distribution being included in here? Well, how these maps behave is that when you take a slice at a given redshift, you are going to weight a given galaxy by the fraction of its photometric redshift PSF, or PDF, sorry, that is within that redshift slice. So if a galaxy only has a very small probability of being at a given photometric redshift, it'll be weighed very, very little in the construction of these maps. And I highly suggest people look at the Darvish 2015 paper for a great comparison between map estimation pipelines that you can use to do something like this. With these maps in hand, we identify different environmental bins that we will be comparing galaxies using. Dense environments are going to be greater than twice the average density at a given redshift. So on this map, that'll be green and red are going to be areas that are labeled as dense environments. There's an intergroup between the average density and twice the average density. That's the dark blue on this map. And finally, there is the field, which is lower than the average density in a given redshift slice. And so these will be galaxies outside of these protocluster regions, very much in the field, not in strong groups. So we have our galaxies selected by stellar mass as a function of redshift. We have an estimation of their local environment. Now we need to estimate the individual galaxies' star formation rates and stellar masses. And to do this, we use the wonderful catalog of photometry available in Cosmos, which goes from the far UV to, in many cases, the far infrared, but at least the mid-infrared in most cases, and conduct SED fits. So here on this plot, we have luminosity of a given galaxy on the y-axis. We have observed frame wavelength on the x-axis. And this is a fitting procedure done using the code magphys, which will take the photometric data points in red, first in the optical, fit an obscured stellar component, and then from that obscured stellar component fit, there is an estimation of how much light was absorbed by the ISM within the galaxy, and that energy will be re-radiated in the far infrared. And so this gives us an estimation for the total obscured plus unobscured star formation rate within a given galaxy. And this is an example fit from a galaxy at redshift 1, where you can see that there is a pretty sizable far infrared component from all of that obscured energy in the optical. Now, this will work for most galaxies, a good 90% of our targets. However, at the massive end of the galaxy stellar mass function, you tend to find many active galactic nuclei, and magphys only includes a stellar and gas component. So how do we account for AGN? Well, first we'll identify cases where magphys does a bad job. This is done by looking at the W4, the IRAC4 band in the original magphys fit. And if it's greater than 40% off, so factor of 0.4 between the model fit and the photometry, we'll be able to say that, okay, there is some sizable component to the mid-infrared that is not properly being fit by magphys, and it's probably due to an AGN. And so we go to the code SED3 fit, which is a modified version of magphys, which includes an AGN component here plotted in the green, with the attenuated stellar component in blue, the dust component in red, and the pure unattenuated stellar component in the dashed gray. And you can see that for this case, going to SED3 did a much better job because that AGN component was able to contribute to the mid-infrared. And this can have significant effects on your star formation rate estimations. We change by, let's see, a factor of 5 when using an AGN model in your SED fitting. So now we have our star formation rate estimates, our stellar mass estimates, our local environment estimates. We can finally say something about how these massive galaxy progenitors are forming stars as a function of redshift and environment. So here's our primary result plot, which I'm going to take a few minutes to go through so that everyone understands where these numbers are coming from. Here on the y-axis, we have stellar mass growth rate. And depending on the line, that can mean subtly different things. So I'll be walking through each of the lines. And on the x-axis, we have redshift. So first, I want to point out the dark green line. That is the growth rate in stellar mass of the average stellar mass of our sample in each redshift bin. So for example, going from a redshift of 2 to a redshift of 1, there is a change in median stellar mass in our sample that is highly driven by our selection criteria. And that is telling you a given solar mass per year rate of change in the total mass of the system. And so this dark green line is telling you something about the total, all reasons included, the total stellar mass growth rate of these massive galaxy progenitors, going from redshift 3 to redshift 0.5. Now, the red and the blue lines are the growth rate only due to star formation, so just from star formation rates, for progenitors in dense regions in red and progenitors in field regions in blue. And you can see that both of these two lines are fairly consistent up until a redshift of 1, after which you see that the progenitors in dense regions have a sharp fall off of growth rate due to star formation, where the massive galaxy progenitors in the field weakly, or we can say level off, but then we only have one more massive galaxy in the field by redshift 0.5. You just don't see massive galaxies out in the field in Cosmos below that redshift because of volume reasons that I mentioned before. So what does this plot mean? Well, first we have an era where the growth rate purely due to star formation is consistent with the total growth rate. You see the blue and the red lines are consistent with the green line. And so we can say that above redshift of 2.2, these massive galaxy progenitors are growing primarily due to star formation. Star formation is doing the bulk of the work. Then we have this intermediate era in between redshift of 1.2 and 2.2, where these lines are no longer consistent. The growth due to star formation dips below the total growth rate being experienced by the sample. And so this tells us that, all right, so star formation is contributing, but isn't everything. There needs to be an additional stellar mass growth component to achieve this green line rate of growth. And then this trend continues at low redshift, where star formation is negligible, is not responsible for the stellar mass growth. So what we can say is that there are 3 eras, one that is star formation dominated, in era 2 at redshift 1.2 to 2.2, where star formation is helped in the stellar mass growth department by the stellar mass deposited due to galaxy mergers, such as major mergers and minor mergers at this redshift. And then at low redshift, many studies have found that dry mergers can be a predominant growth mechanism for BCGs. And so we find that this result is consistent with what's expected, that star formation just is not at all important to the stellar mass growth of massive galaxies below redshift of 1. So there's one last line that I didn't talk about quite yet. That is the dashed gray line. If you took the merger stellar mass deposition rate from Illustris, how much stellar mass per year is being deposited onto these galaxies at a given redshift, at their given mass, and illustrious, what would that growth rate be? At 100%. So in a merger, 100% of each of the galaxies' mass is being added to the joined system. That is that gray line, which you can see is actually slightly above the total mass growth rate that we see. Now, one of the caveats about this line and why I don't accentuate it too much is that that 100% efficiency rate that I mentioned isn't quite true. There are many works trying to understand how efficient mergers are and what the fraction of stellar mass unbound from galaxies during a merger is. That rate can, that unbound fraction can change dramatically depending on the paper. I've seen rates as high as 50%. So imagine that there's a factor of, almost a factor of 2, where this gray line can be lowered. And that's the total stellar mass being added due to mergers. So overall, the takeaway from this plot is that we've been able to identify 3 eras of massive galaxy progenitor growth, and local environment is not a concern to these galaxies above a redshift of 1.2. If you're a massive galaxy, you are encountering star formation rates and growing your stellar mass very similarly, depending on whether you're in the field or in a dense protocluster region. We did perform some additional tests on the sample, looking at the color evolution of these progenitors, and what you can see is what is expected. They move on this NUV minus R minus J color plot from a star-forming region, which you can see on the bottom and the bottom right, into a quiescent region in the top and the top left. Effectively around that redshift 1.2 area, that's where a very large number of these progenitors move into this quiescent state. We also looked at the Sursic indexes for each of these indices for each of these galaxies using the morphology measurements that have been done in the Cosmos field. Unfortunately, the errors are much too high. Just the spread of values is much too high to actually say something. And we're only able to have a very large number of Sursic index measurements out to redshift 1. You see the color bar goes away above redshift 1.5 because there just aren't trustworthy Sursic index measurements at that high redshift. Now, we also looked at the diskiness of these galaxies. Human beings have gone through each of the postage stamps of these progenitors to identify whether there's a disk or a spheroidal component or both. And what we find is that the galaxies in the dense environments tend to be much more spheroidal than the ones in field environments. And also the quiescent galaxies, again, move towards the spheroidal morphology, all very much expected. So the very big result from this paper was that these massive galaxy progenitors grow through 3 phases that are consistent with the observed merger rates if you allow for a large fraction of unbound mass. But these star formation growth rates are independent from environment until very low redshift. And that's the big takeaway. Because there have been several different works trying to understand whether or not environment matters at high redshift, because you have a very different dynamic range of densities at high redshift. And we now have one more result voting for the environment really is in very strong consideration at high redshift camp. So you can ask, well, how does this compare to the general population? We were just looking at the very high mass end, above 10 to the 10.5 or 10 to the 10.1 at some of our highest redshift bins. Let's look at a much wider sample. So to understand where we're going with this, I have a very quick review of something called the star formation main sequence. This is a name that has many different other names, called the galaxy main sequence, the star forming main sequence, many different names. What matters is that it is a tight, highly correlated trend between the star formation rate on the y-axis and the stellar mass on the x-axis. So for a star-forming galaxy, if you are of a given stellar mass, there is a very narrow range of star formation rates that you are going to spend most of your time on while you're star forming. There may be times where a galaxy is in the starburst regime, like a factor of 3 above the main sequence, where they are forming a profoundly higher amount of stars. Or once they consume their gas supply, they may descend through this intermediate region called the Green Valley into a quiescent region well below the main sequence where they have stopped forming stars. And that's where brightest cluster galaxies in the present day universe will reside. Now, you shouldn't treat this as like railroad tracks where a galaxy just proceeds up the slope. Galaxies are chaotic things, and so you'll see them go up and down in simulations. So what the main sequence is telling you is the bulk properties of a large population. Now, the shape of the main sequence has been observed out to a redshift of 2.5, often observed with a knee at high mass, where galaxies will form less and less stars with stellar mass. However, local environmental effects have only been observed out to redshift 1, and things are still highly debatable for this general population at higher redshifts as well. So we used a very similar pipeline to our BCG progenitor work to select all of the galaxies above the stellar mass completeness limit in the Cosmos 2015 catalog. So here is a look at that total sample in terms of density plot. So that you're looking at 118,000 galaxies that lie above the stellar mass completeness line that rises in stellar mass with redshift as expected. As at high redshift, you are only expected to see the really high mass galaxies. And what we do is we estimate their star formation rates using SED fits and plot our trend in comparison to others of the literature. So here is what looks like a complicated plot, but it's really just many copies of a plot that I just showed you. It has star formation rate on the y-axis, stellar mass on the x-axis. Each of these squares is a different redshift bin, going from the present day universe in the top left to high redshift universe at around redshift 3 in the bottom right. The median star formation rate at a given stellar mass bin for our sample is in the dark orange line, and we plot many other trends for comparison. Now, the main sequence only works if you're selecting just star-forming galaxies. So we selected galaxies that are star-forming using NUVRJ colors and that are above this specific star formation rate cut that is above 10 to the minus 11 at low redshift and evolves with redshift to higher and higher specific star formation rate values. This guarantees that we're just looking at star-forming galaxies at a given redshift. Now, what you'll find is that our fit has a bit of a need to it at high mass. So what we did is we followed the functional form of the Lee et al. 2015 paper, which is this broken power law where you have a knee at high mass, but we allowed all the parameters to be free. So in cases of high redshift, where you can see the star forming population is not quite as resolved in comparison to everything else, we actually end up rederiving a linear main sequence at high redshift. So this is just setting up the main sequence trends for the total population. What we see is fairly consistent with other works. We find that we're slightly below many other works, potentially because of the difference between delayed and instantaneous star formation histories included in the SED fits. We're still looking at some of the details of that, but we think that it's due to that. So let's split up these populations due to environment. Let's look at our main sequence as a function of local environment, and also look at our quiescent sample, which is this group that you can see below the specific star formation rate cut. See if that changes with environment as well. This is a very similar plot. Again, we just split due to environment, with errors being the error on the median. The dark blue is star-forming galaxies in dense regions. Light blue is star-forming galaxies in field regions. Red is quiescent galaxies in dense regions. Purple is quiescent galaxies in field regions. And what you see is, well, the quiescent galaxy star formation rates are extremely low. They're below our cutoff, which is expected. That's by construction. But they're consistent across environment. And the star-forming galaxies, what we see is that independent of environment, they are very well consistent, which is very interesting to us. Because this is telling us that even out to lower redshifts, you're not seeing very much of a difference in the star formation rates of galaxies in dense environments versus field environments at large scales. And so the quiescent galaxy populations that we often see in galaxy clusters is primarily due to number statistics, that star-forming galaxies are just very quickly, and this is one of the results from these trends being consistent, the transition from star-forming to quiescent has to be very fast when environmental effects take hold. And so we have this very important result that local environment really isn't having much of an effect at any stellar masses at high redshift. And right now, our next steps are reducing all of the publicly available WFC3 images from HST on the MAST archive to build a new, larger morphology catalog to let us know what the bulge to disk luminosity ratios of these targets are, because it's a very important consideration to understand, well, how big of a role is these star-forming disks playing in these samples, whether they be star forming in dense or fields regions. We want to understand whether their structure has any difference as well. And so that's taking quite a bit of computation time, but we're almost there. So stay tuned. Now, this has been primarily my dissertation work on massive galaxy progenitors. As part of my postdoctoral work, I'm going to quickly go through how we're trying to understand how an AGN hosted within a galaxy can shut down the star formation of their host from within. So instead of the local environment trying to play a role in shutting down star formation, what if it's something within the galaxy, such as the active galactic nucleus? I've been working with Dr. Alison Kirkpatrick on a new population of quasars called cold quasars that were a population of unobscured quasars in stripe 82X field. And these are very interesting targets. They are bright in the X-ray, so we know that they are unobscured AGN, where we're seeing much of the X-rays coming from the inner regions of the central engine. However, these are galaxies that still have a significant cold dust component because we've detected them in the far infrared. And so this is telling us that these cold quasars are a very rare population where the cold gas supply still resides within the galaxy. And what's been found is that these host galaxies tend to be far above the main sequence with hundreds to 1,000 solar masses per year. So these are galaxies that are forming a profound amount of stars, but are likely not to for very much longer. And their stellar masses are pretty close to, in this original sample, pretty close to the high mass end. But we are opening up that mass range with some of our ongoing work. Here is an example image of a cold quasar from SDSS, or sorry, this is DECCAM, my apologies. It's a GRZ composite. And what you see is not much. This is a stamp where the central engine is overpowering the host galaxy in optical light, so you're really just seeing a point source. And that's making it very difficult to understand the host galaxy properties. So to better understand the host galaxy properties, Alison applied for and won some time on Sophia to better constrain the far infrared SED of these targets so that we can understand what the temperature of the gas and dust is in these systems. And during this proposal, we lowered the X-ray cutoff, but still kept this requirement that they be these far infrared detected targets. Now, time was won on Sophia. For the students in the talk, here is an image of the Sophia Telescope in the bottom left. It is a far infrared telescope that is built inside of a plane. So it's utterly fantastic and amazing piece of engineering. On the right is a picture that I took from the parking lot in California, awaiting my turn to go on board Sophia as part of the observational program that we had. Unfortunately, during both of the nights that I was there were engine difficulties that prevented observations from being taken. So for many targets, we were not able to get far infrared observations. However, very quickly after I flew home from California, we were able to get observations. One of the targets was observed, and we got a strong detection from cold quasar 4479. This number is coming from an internal catalog from Stripe 82, so that we can keep all of these candidates straight. Again, we have an optical composite image on the right showing you that this is a galaxy with a strong point source in the center with a very blue color. But there does seem to be an asymmetric red component to the galaxy that we don't quite understand quite yet. And we find a very, very strong emission at 89 microns, 75 millijanskis, so signal to noise of 5, out at 89 microns. Now, some of you may be questioning, Kevin, why are you so excited about this 89 micron detection? Well, this does wonders for helping constrain the fits from SCD fitters. So here is a plot of cold quasar 4479 in our paper that was submitted very recently. Again, the red points are the photometric data points of our target. This orange diamond that you see is the Sophia detection. And we used 2 different SCD fitter codes to compare results to see how well each one did. Seagal is one SCD fitter, which we ran both with and without the Sophia detection. With Sophia is the bright, solid green line in Seagal. Seagal without Sophia is the dashed dark green line. You can see a very big difference in the far infrared peak behavior. Again, we used SCD3 fit because we know this is an AGN. The fit with the Sophia point is in the dark black. Fit without the Sophia point is this light gray. And so this is me just saying how amazing Sophia is to a far infrared group who probably agrees with me. So what we see is that Sophia observations have a very powerful way of constraining the far infrared behavior. And what we find is that these more accurate fits give star formation rates around 78 to 95 solar masses per year in star formation. So this is great news. This is telling us that this is still a star-forming AGN host. And thanks to the SDSS spectra available for this target, we're able to better constrain the growth rate of the black hole as well. So we're able to perform spectral line fitting to the O3 optical emission line. Again, we also have the X-ray data from Stripe 82, so we have a black hole mass growth rate from the X-ray emission as well. I plot both of those as 2 different lines on this plot here on the lower right. Sorry if I'm going a little fast. I only have one more slide left. On the y-axis is the it is the mass of the black hole in solar masses, the central supermassive black hole. On the x-axis is stellar mass in solar masses of a comparison broadline AGN sample from Sun et al. 2015 and our cold quasar 4479. You can see that it lies within the median trend found in broadline quasar samples, where the black hole and the stellar mass are growing in lockstep. And you can see that depending on the estimation method, whether using O3 or X-ray to measure the growth rate of the black hole, this galaxy is still very consistent with the median growth behavior of the black hole and stellar mass for broadline quasars. So our future work is delving into how these cold quasars connect with other galaxies with hot dust components with AGN, such as red quasars. We're trying to understand whether we're looking at objects at different points in time in their evolution, or whether they are looking at different position angles, for example, in relation to the AGN. There's so much work being done right now on this very important phase of AGN growth and star formation shutdown that we're trying to do our best to make sure that we have a cohesive picture comparing these different classifications that many other people are doing great work on. So to review the work that we've talked about today, we find that very massive galaxies in the present day universe, like BCGs, can exhibit rare episodes of star formation. However, they are predominantly very quiescent. Massive galaxy progenitors above a redshift 1, however, are much more diverse in terms of ellipticals and some irregulars that are star forming, going out to redshift of 2 and 3. However, local environment really does not have a strong effect at high redshift, either for these high mass cases or low mass cases. And finally, we are making some important headway in understanding the critical evolution phase where an AGN is shutting down star formation in a massive galaxy, and there's plenty of work to be done there. So you can find some of my contact information at the bottom of the slide. Thank you very much for listening.
Thanks, Kevin, for a really great talk. So now begins the Q&A portion of our webinar. So you can submit all of your questions again through the chat window. If you can't find the chat window on your screen, go to the bottom of the Zoom window and click on chat, and it should bring up the chat window. So you can type your questions directly into the chat window there. If you'd like to ask a question to the speaker directly, you can use the raise hand function through the participants window.
And while people are typing, I want to make one quick advertisement. So many of us are having quite a lot of difficulty working from home and trying to mentor students in this new paradigm. So some of us at KU and RIT put together an astronomy seminar participation guide and reading guide, teaching new undergraduate and graduate students how to look for astronomy papers and how to read papers, and then how to present papers at your local journal club, Astro Coffee, however you decide to name it. So as we barrel towards a semester that is approaching, please take a look at this archive number. We want to make the astronomy community's job easier. So we hope that you find this useful and you can forward it to your students to take some of the load off of trying to get new students up to speed in this new environment.
That's really great. I think while people are thinking, I wanted to ask you a question, so I'll use my prerogative as moderator. I had forgotten to mention when I introduced you that you ran one of the JWST master classes this past spring.
Yes.
And so I was A, curious kind of, if you had any take homes from that experience, and B, whether there were directions you were hoping to go in your own research to follow up and use JWST.
Yes, so JWST is going to be an incredible piece of technology, and like any incredible piece of technology that has so many different ways of observing, it is a very, very complicated thing to do exposure time calculations for. And so one of the big takeaways that I had when I was trained at STSEI and that I gave to my attendees was, if you think that you have exposure time experience with Hubble, that is not quite valid for getting yourself started with JWST. There's so many more options, so many ways that you can customize your observations, that really the key is getting started and asking for help from the STSEI help desk, which is always there to help you. But the earlier you get started, the faster they can respond to you and answer questions. For my own work, I'm very interested in the morphologies of galaxies at high redshift. So the NIRCam observations that'll be coming out of JW once it launches, that's what I'm waiting on. It'll be great. And then there's also work that we're trying to nail down regarding the cold quasar sample and trying to see exactly what filters from JWST would do the best job at constraining some of the hot dust behavior in these AGN systems. So that's really what we're working on right now.
Okay, great. So we'll give people another minute or so to put some questions into the chat window. I'll take this opportunity, since we're getting towards the top of the hour anyway, to advertise that we have these webinars every month. They typically happen about this exact same time, so we schedule them for the first Tuesday of every month at 1 p.m. Eastern or 10 a.m. Pacific. And so, I hope that you'll consider joining us for future webinars. And of course, we are always looking for speakers for our webinar series. So if you yourself would like to be a speaker, or you have someone you think would be a great speaker, please reach out to any of us on the IRSIG Leadership Council and nominate yourself or nominate your colleagues, because we are especially excited to kind of get suggestions for early career scientists from diverse backgrounds and get a really great pool of speakers for our webinar. So I don't see any more questions coming into the chat window right now. So I'll say thanks again to Kevin for a really excellent talk. I really enjoyed it. If you still have questions, please go ahead and type them into the chat window. We'll kind of hang on for the next couple of minutes until we get past the hour mark.
Yeah,
and otherwise, hope to see you all at a future webinar.
Yeah, thank you very much for attending. And if you have any questions that you think of later today, email me, find me on Twitter. I have my contact information up right now.
Great. Looks like we have someone who would like.
Yes, thank you very much for the feedback. Okay. Yeah, go for it.
Hold on. You should be unmuted. Okay. I think you're unmuted if you want to try and ask your questions. Otherwise, I'm sure Kevin would be happy to respond to an email if you send him an email after the end of the talk.
Yeah, definitely. Take a screenshot of my email. Just reach out. I'd be happy to answer questions.
Okay, great. Then I think otherwise, since we're at well, 12 for me, but the top of the hour for everybody, I'm going to go ahead and stop the recording.